Okay. Practice exam 2. So this practice exam has 8 problems. Each is worth 10 points. And I'll say this. It's a good idea to try the problems out for yourself before referring to my solutions or Nagi's solutions. It's very helpful that you go through the experience of um, working on the problems for yourself, getting stuck, and then getting unstuck. But that said, let's begin. So problem number 1, I'm going to just grab it from my other screen and paste it in. Alright, so number 1, whoa. So we want to find the equation of a circle centered at this given point, passing through the point 3, comma, -2. My cursor kind of got in the way. So for this one, well, we've done a homework problem that is quite like it. The thing you need to remember is what's the formula for a circle centered centered anywhere. So you should remember it's x minus h quantity squared plus y minus k quantity squared is equal to r squared, where the h and k correspond to where the circle is centered at. So this equation says that the circle is centered at the point h comma k. And this part says that the radius is r. So a circle of radius r centered at h comma k, that's what this equation represents. Now to do this, well, there's 2 ways to go about this. One way involves figuring out what the radius length is by doing a distance formula between these 2 points. But the class has told me that there's another way that involves plugging both of these points in, which is valid. That will also work. So let's plug both of these points in, and let's see what happens. So Z is my center. I'm going to plug that in, and for H and K. And P, I'm plugging in for X and Y. So when I plug this in, let's try to do this. Oh, maybe I'll... So 3 and -2 are my x and y, and then we're going to get r squared. So h is supposed to be negative that, so it's going to become +2. And then k, it's going to become -1. So just in case it wasn't clear, this I'm letting be the x comma y, and this I'm letting be the h comma k. And you'll see that this indeed matches up. We just have this sign flip happen because this value for h is negative, we have negative, negative. Okay, and this will let me solve for my r. Okay, so 5 squared plus -3 quantity squared. So we get 25 plus 9, that's going to be 34. So my r squared is 34. Okay. Yeah, that looks right. Okay, so then lastly, we want the equation of the circle. So now I only plug in my h and k. So x plus 2 squared plus y minus 1 squared is equal to 34. And that's my equation of the circle. And I should comment that I'm doing this for the first time. I haven't looked at these problems. Well, I mean, I've glanced at the problems, but I haven't, prepared them. So if there are any mistakes, hopefully I catch them in real time. Otherwise, they'll be noted in the description box. Okay, I'm going to copy number 2 now. Let's see. All right. Number 2. All right, so we have, this is really similar to a homework problem from the past. We have on a line, we have a point. We want to create 2 new lines, one which passes through the point P and is parallel to the given line, and another one that is perpendicular. So the approach that I suggested was it was more of the approach that you will have seen in other classes, where we get the slope of the given line, and then we construct the new line using point slope form. So, well, as a refresher, let me just comment what point slope form is. So point slope form, the strength of this format of line is that you don't need to do too much arithmetic. You just need the point and the slope, and you can then write a line given that information. So this is what point slope form looks like. M is the slope, and this x0, y0 is the point that you want the line to pass through. So it looks something like this. So when you plug values into this format of a line, you're guaranteeing that the line is going to pass through this point, x naught, y naught. And so that's what this point, minus 2, comma 3, is going to be plugged into. What we need now is the slopes of the lines for A and B. So we get that information from the given line. And to do this, we want to manipulate this line, or this equation. So I'm going to do a bit of algebra to this. I should probably do this step by step. So first, let me subtract 5x. So we have 6y then is equal to 7 minus 5x. And then I should divide the 6. So then we get y is equal to, well, I don't like writing it like that, so I'm just going to rearrange this. And then we get negative 5 over 6x plus 7 over 6. Okay. Is there a better way I can explain this? Well, yeah, if I didn't write it like this, if instead I wrote it as, if I wrote it as minus 5x plus 7, see that we could subtract the 5x from both sides, but then we put it in front of the 7 there. Then we would end up with this, then we divide the equation by 6, divide both sides by 6, and you get this, right? And so what's the reason we do all of that? Well, we wanted the slope, which is what I'm boxing in green. Okay, so we found that the slope of the given line is negative 5 over 6, and so that lets us solve A and B, right? The part A, we want a line that is parallel to the given line. That means that it has to have the same slope as the given line. So for A, maybe I will switch back to black. So for A, we want the same slope. We want m is equal to negative 5 over 6, and we want it to pass through the point negative 2, comma 3. And so we just take that information and we plug it into the point slope formula. So that'll be y minus 3 is equal to m, negative 5 over 6, x minus, well, in this case, x naught, so x minus negative 2. That's going to turn into a plus, x plus negative 2. And I would say that if I saw this, this work, I would be okay with it. Like, I don't need to see the student change this anymore. It doesn't specify what format the answer should be in. This is completely valid as an equation of a line. You could also, if you wanted to, you could write it in standard form, or you could write it in slope-intercept form, but that would just require you do a bit more arithmetic, and so I would suggest not doing that. Okay, for part B, we want, this time, we want the line to be perpendicular and pass through the point. So the key thing we need to know is that for perpendicular, how do I want to say this? The property that a line, the property that happens with the slopes of the lines, going from a line to a line that is perpendicular, what you get is, what you need to do is go from m to the negative reciprocal. So if your given line has slope m, then a line that is perpendicular to that given line is going to have a slope that is the negative reciprocal. Right. So, for part B then, the slope that we want our line to have is the negative reciprocal of the given. So in this case, it's going to be 5 over 6, or 6 over 5, sorry. And then, of course, the point that we want it to pass through is the same point. And all that happens to the equation of the line is we just change the slope. 6 over 5, and then x minus x naught, which, just like before, negatives will double up and become a plus. So we get this. Great. Let me go ahead and box this. Okay, number 3. Let me copy it. I messed up. Escape. Okay. Come on. All right. Oh no. Good. All right, so we have two vectors. We want to find this vector w. That is a I don't want to use that word. Well, it's we do some arithmetic to the given vectors and we get the vector w. And then we also want to find the magnitude. Use exact values, and units are going to be miles. So the miles part, it only applies to this magnitude. Okay. So the vector arithmetic is how do I explain it? It's component wise. Is that a way to explain it? So you just do the arithmetic to each of the components. That's one way you can phrase this. So let's see. What do I mean by that? Well, first let's substitute in the vectors that are given. So 4 times the u vector minus 5 times the v vector. Okay. And so what does it mean component-wise? Well, what I mean is that, like, you can take this first component, and usually you would call this maybe the x component, and then the second component, you could call it the y component. And so you're basically doing two calculations. One with the top row, but you still have this 4 times the top guy minus 5 times the top guy, and that's one calculation. And then you've got the bottom calculation, 4 times the bottom minus 5 times the bottom. So you're doing two calculations, and that's what I mean by component-wise. You can split it up into the top part and the bottom part. If your vectors had even more components, like if it had 3 entries, or you could imagine it have like 10 entries or something like that, then it would proceed in the same way. You just do the calculation 10 times or however many times. The reason you would do that is only because, like, if you're working in a higher dimensional space, but here we are only working in a 2-dimensional space. Maybe 3 dimensions is more realistic because we live in a 3-dimensional space. But that's fine. Okay, so right, let's go ahead and calculate this. And well, one way to do this is to actually put the to multiply to scale up the entire vector. So we could multiply the 4 to both of these entries, which effectively is scaling the vector up by 4. You could imagine, like, if you drew this on a coordinate system, this is x3, y -2, and then you just take that vector and just scale it by 4 copies of itself. That is one way you could think about this. And then, well, let's multiply the 5. Okay, and then -5 like that. Now we have this negative, so that's 12 plus 10 is going to be 22. And then -8 plus 5 should be -3. Yeah, so that should be right. -8 plus 5. Yep. 12 plus 10. I'm pretty sure I didn't do anything wrong. Yep, that looks good to me. Okay, so that is the first part of this problem. The next thing it wants is the magnitude. So don't forget that. So we're going to use it's kind of distance formula, right? So what you should remember about I don't remember if you learned this for like more than just 2 dimensions, but let's try to talk about this in terms of just 2 dimensions. So if you're given a vector v with x coordinate and y coordinate, like so, then the magnitude, the way you calculate the magnitude or the length of that vector is you use Pythagorean theorem. You use the distance formula, which is the square root of the components squared and then added together. So this is the formula you'd use, and I just want to make a little comment because I do want to just generalize this a tiny bit in case anyone goes on with math. If you have more components, what this generalizes readily. So you just end up doing a more generalized Pythagorean theorem, a more generalized distance formula. You square each of the components, add them together, and then take a square root at the end. So you see, the only thing that happens is we have to then tack on this plus z squared. But most likely we're going to only require that you know this guy, because I don't think I remember seeing us work with vectors with higher dimension, but that's okay. All right, so that's what you need to use, and we use that with this. So, well, this calculation might be a little bit bothersome to do by hand. I'll try to do it. I'll try. So, square root of 22 squared plus -3 squared. So, 121 times 4. So, okay, so I'll tell you what I'm doing. 22 I know is 2 times 11. So then when I want to square this guy, I'm thinking about squaring this guy. So I'm thinking 4 times, and I know what 11 squared is. So so that tells me this is 484. So 484 plus 9. Okay. Let's see. So that's 493. Yes. Does this simplify? Do I want to care about it simplifying? I will accept it like this, but you know, it's possible that this can reduce a little bit. But I don't see it. It would take. I mean, I wouldn't take points off for that. That's acceptable to me. So I'll just box. Oh, one thing. Yeah, so exact value, so that means you can't just plug this into a calculator and get a decimal. We want it to be exact, so it had better be in some radical format. Don't do any numerical approximation. But then also miles, right? So I should maybe put that in underline. So this is in miles. I should say miles, or MI as an abbreviation. Okay, and there we go. So now no points are taken off. That's good. Right, so that was number 3. Okay, almost halfway. Number 4. Copy, paste, and let's go. Theta is an angle. We have a point. Okay. Find the exact values of the 6 trig functions. Great. So, well, let's do a little sketch because I want to figure out what quadrant this is in. So -15 is going to be somewhere over here. -15, and 8 is going to be up here. 8. So I have a point that is around here, a point here, and my triangle is going to be like this. And if I were to label my sides, so now this is where I've written -15 in the wrong place. So if I label my sides, maybe also just to help, I'll use a different color. So this side is of length 8. This side, I want to think of it as 15 negatively. We're doing a little shortcut, I guess, where we kind of allow the sides to have negative length. It'll help with reading the values off. And then, what is the remaining side? Well, I have to, either you remember this Pythagorean triple, or you forget, like me, and have to compute it by hand. So let's compute it by hand. So let's see, 8 squared plus 15 squared, 64 plus 225? Yes. 200 and looks like 89. Yeah, 289, and that's 17 squared, isn't it? 49. I'll check just because it's been a while. 9, 4, 7, 1, 1, 7, 1. Yes, 289. Okay, so yes, this is 17. Great. Okay, so now that we have that, we can fill out, or we can find the exact values of all the 6 trig functions. Okay, so sine, cosine, I'll give myself a bit more space, I think. Cosine, tangent, and I should also mark where my angle theta is. So, well, here's the thing. I do want to be a bit more precise about what I'm saying. So, this angle in blue is the actual angle theta stated in the problem, because it's the angle to this point P. But the reference angle, the angle we actually think about things in terms of, is going to be this angle in red. Okay. Alright. And so let's see now. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And notice this is where I use the fact that the 15 I think of negatively. And then tangent is opposite over adjacent, which also uses the negative 15, so we know that tangent is negative for this quadrant. And then let's do the other 3, although it just involves reciprocation. Cotangent theta. Okay, so this is 17 over 8. This is 17 over 15 negative. And then this is negative 15 over 8. Let's put that negative a little bit higher, a little bit larger. Okay, there we go. Right, so that is number 4. Is there anything else I want to say about this? Not sure. Well, we went through these problems. This was on the most recent homework. Was it homework 4? This is the homework that we went through. I think it was homework 4. I'd have to find it. That's okay. All right. The next problem. Oh no. Next problem, number 5. Okay. Right. So 660 degrees. Find the exact values of all 6 trig functions. So what I'm going to want to do for this is reduce that angle by subtracting off copies of 360, because this is wrapped around the unit circle at least once. So let's minus 360 degrees from that and see what we get. 300 degrees. Aha. Okay. So we could also subtract off another 360, because yeah, let's do it one more time. 360, because we get then negative 90, negative 60 degrees. That's more easy to think about. Where do I want to put this? I'll put it over here. So we know that we're in the 4th quadrant, and we're a 60-degree angle in the 4th quadrant. Right, so that's what the picture looks like. And if you remember your unit circle, you actually know. Let me do it like this. It doesn't specify theta, so I'm just gonna write 660 for everything. Cosine, tangent, okay. So let's start with these three. So for this, first, I think about the representative angle, right? This 60 degrees is the representative angle, although the actual angle to work with is the negative 60 degrees, because this one is equivalent to the 660. The 60 degrees being the representative angle just means that it's the correct value up to sine, up to positive or negative. So for these three, I think about what the function will evaluate to at 60 degrees. So sine of 60 degrees, well, if you remember your unit circle, you'll know this is 3 pi over 2. Cosine of 60 degrees, if you remember the unit circle, you know this is 1/2. And then tangent of 60 degrees is going to be root 3. Okay. Now, this is almost correct, okay? Because we were thinking of 60 degrees, not the actual angle, the negative 60. So now we need to think which of these functions ends up being negative. And so, well, one way that I explained it in class was that cosine corresponds to the x. No, I don't really want to put x there. Cosine corresponds to the x-axis, and sine corresponds to the y-axis. So that means that for these two, cosine is positive. For these two, cosine is negative. And sine, being the y-axis, means that for these two, sine is positive, and for these two, sine is negative. Okay. So that means that the quadrant we're actually thinking of is this guy, the fourth quadrant. And so cosine is positive, but sine is negative. So we need to have the negative. And I'll do it in a different color just to emphasize. This guy needs to be negative, and then the tangent needs to be negative. Okay. Because the tangent is sine over cosine. You can also remember it from well, it's a set of diagram or pictures that I've written it in class a couple times, where like sine is plus plus minus minus, cosine is plus plus minus minus, and then tangent is alternating plus minus plus minus, like that. But you can get this from thinking of like dividing sine and cosine, or even multiplying, actually. We'll do the trick, because minus times minus gives you plus, and you can check the other quadrants. Right, and then the last thing for this problem is to do the other three functions. So cosecant 660 is going to be negative 2 over root 3. Secant of 660 degrees is 2. And cotangent of 660 degrees is negative 1 over root 3. And I will box this. I'm just doing a quick check to make sure I didn't make any mistakes, because this is the first attempt I've made on these. So yeah, that should be right. Yeah, good. Okay. Number 6. Verify an identity. So this identity looks rather similar to one on the homework, I think. Yeah, your homework only had a couple of these identities. Okay. So let's see what happens. cotangent, cosecant, and sine. Well, so I can't plan this ahead too much. The only thing that I'm seeing is this cotangent. I would want to break this up into sine and cosine. So let's manipulate the left-hand side. Maybe we can also manipulate the right-hand side. Cosine x, cotan is cosine over sine. Ah, okay, now I see it, I think. Yeah. So I'm just trying to divide things. So here, you see that the cosine and cosine are going to become cosine squared. And then you have a sine squared, or sine x. But then we have this as a fraction, and we want to combine the sine into it. So we need the same denominator, which means that we multiply top and bottom by sine of x. So this becomes sine of x we can rewrite as sine squared over sine. And then we can combine the fractions. And when we do that, we get sine squared x plus cosine squared x over sine of x. And now this numerator, you should remember your Pythagorean identity. So sine squared plus cosine squared is equal to 1. So then it's 1 over sine. And then use your reciprocal property. So you know that the reciprocal of sine is cosecant. So I guess I'll go down one more. And that is how we end up getting the right-hand side. And so there we go. We've achieved what we were set out to do, which is to verify this identity. Okay. Number 7. Oops. Find the exact values of just sine and cosine, given cotan is that. Okay. Right, so I think this is one of those common mistakes that we've seen, or that Nagi has tried to mention on his slides. So don't get misled and think that you can just do something like, let's just do a warning, I guess, first. Warning. Don't do this. Where like you think this cotangent is equal to cosine alpha. Is it alpha? Oh, alpha and theta. Oh no. Yeah, no, they should be the same angle. They should be the same angle. That's a typo. But yeah, don't split it. Don't split it and then think like don't think that that's the case. No, don't do this. Don't do this. Don't do that. Right? I mean, the identity is true, but you're not gonna be able to pair things up and get like cosine alpha equals 7. That's complete nonsense because sine and cosine are always bounded between -1 and 1. So that gives you nonsense. Instead, let's see. The right way to do it. Cotangent alpha. It's kind of distracting. Let me just fix that. This is supposed to be. Let's use theta because I think everyone is more comfortable with theta. So instead of that, we'll use theta. So instead, we're told it's supposed to be in the third quadrant, and okay, no. Right, so whatever the angle is, so this would be the actual angle, theta, But of course, the angle we want to consider is this internal angle to our right triangle. And let's see. I'm trying to make that a point. So instead, what we want to think is that cotangent of theta is the reciprocal of tangent. So instead of opposite over adjacent, it's adjacent over opposite. And that we want to think of it as 7 over 1. So we can let our adjacent side be 7, and we can let our opposite side be 1. And in fact, for these guys, it's actually supposed to be negative, because this point that I've drawn, let me switch over, this point here, it has both x-coordinate and y-coordinate negative. So that means that these sides, we should view them negatively. And now the hypotenuse, we can calculate through Pythagorean Theorem. So 1 squared plus 7 squared is 1 plus 49 is 50. And then we want to take the square root of 50. So square root of 50, 25 is inside of that. So this does reduce. You get 5 root 2. But you can use square root 50 if you want. But I'm going to use 5 root 2. Hopefully that's readable. Okay. Right, and so we wanted to find the exact values of sine and cosine. And we've now labeled our triangle correctly. So I can then say what my sine is and what my cosine is for this given angle. So sine is opposite over hypotenuse, so -1 over hypotenuse, 5 root 2. And my cosine is adjacent over hypotenuse. Yeah, that looks right. And one thing I should say, is why is it that this guy, for this is incorrect, but this is fine? Why is that the case? So the thing is, this kind of saying that this side can be, you can put it as 7, this opposite side you can set it to be 1. The reason is because we're actually dealing with a whole family of triangles. We're allowed to scale our triangle up and down. And so that's why we can just let the scale factor be 1. Or you could also imagine, like, you could let the scale factor be 2, or any number that you want, as long as it's not 0, I guess, or negative. And then you just get a larger triangle, but you still have like that these ratios end up being satisfied. And these trig functions are all about the ratios of the sides. So we are able to pick these things out because we're just picking out a triangle from a whole family of triangles that are being scaled up and down. But that's not the same as this kind of operation. With this kind of operation, you end up saying something about the trig functions, and you end up breaking things up in ways that are quite invalid. So there's a difference. Okay. Okay, was that 7? That was 7. Oh wow. So this is the last problem on the practice copy. And it's only been like 40 minutes. Nice. All right, last problem. Consider the angle. Quadrant of beta. Okay. So this is similar to a homework problem. Actually, this is kind of 2 homework problems on our most recent set of problems. But it's like the 2 problems got smashed together. So you have this one where you have to figure out what quadrant this angle lives in, and then you have to do a shift to that angle. Well, let's start by figuring out where alpha lives. So, both sine and cosine are negative. So if we come back to our little diagram of how sine and cosine work, it's like this. And so for sine and cosine to both be negative, that means that you've got to be in this quadrant, the third quadrant. Okay. So now we know where our angle is. And we'll draw the representative triangle. And, well, this, the way I've color-coded things in the past. So I used red for my reference angle, but I used like blue for my actual angle. So let me try to leave it in the same format. So this angle in blue is alpha, but the red is the angle we'd like to think about things in terms of. And let's now split things up. So split up these values. So sine is opposite over hypotenuse. I know this is going to be negative 24, 25, and this is negative 7. So this is the correct labeling for the triangle based off of these two values. One thing you can also check, just like a quick sanity check, is that 7 squared plus 24 squared is equal to 25 squared. I mean, this I wouldn't do by hand. I guess, well, I do have a calculator. I can just quickly check that that's actually the case. So 625, I know that is 25 squared, so we're good to go. Right, so that is just a sanity check. All right. Now what? Well, we want to think about beta, not alpha. We want to think about pi minus alpha. Right. Pi minus alpha. How do I conceptualize what that's doing? Well, okay, there are alternative approaches. I know, for instance, that there's formulas. So I know that we have formulas. So we could use the formulas here, but I want to avoid that first, and then maybe we can talk about using the formulas. But pi minus. Okay, well, I think, okay, yeah. I need to split this into parts. So this is also like, the homework had it nicely because it actually gave you like all 4 different quadrants. For this one, I need to have an intermediate angle that I think about, which is negative alpha. I think I need to think about negative alpha, and then I need to add pi to it, because otherwise I can't quite see what I'm doing. Negative alpha is going in the opposite direction to alpha, so it will end up being in this quadrant instead. Negative alpha is going to go like this. And the labeling, you could do, I guess I should do it just to make everyone be able to follow along. So this will be 24, this will be 25, this will be negative 7. The reference angle would be this one. So yeah, again, we go from alpha to negative alpha by just reversing the direction of the angle. And then we add pi to it because I can view this as minus alpha plus pi. And it's easier for me to think about it in this way. Because adding pi is adding half of a revolution. When I add pi, what's going to happen with this diagram is you just imagine that you rotate this halfway around, and this triangle is going to wind up over here. So, let's redraw some coordinate axes, and my angle is now going to be over here. And so this is now the triangle, and that's the reference angle. Now pi minus alpha is still a little bit difficult to think about. Minus pi is this way, plus alpha goes here. Yeah, in a way. Yeah, that's the tricky thing. I don't really like this, but yeah, alpha, if you actually are careful about the direction, this would be pi minus alpha. If your alpha is going this way, you end up going the other way. Then you add pi to it. You add pi to this angle, you're still going negatively. Yeah. I mean, it ends up not really mattering. You could have thought of it as the other direction, but I'm just trying to be a bit precise about it. Like going this other way around, it's an equivalent angle, so the trig functions aren't going to they're not going to see the difference. Okay, let's go ahead and label. So we take this triangle and we rotate it, or you could imagine rotating. No, well, okay, yeah, that's another thing. So this one to this, it's going to be a reflection, actually. It turns out that going from alpha to pi minus alpha is a reflection about the y-axis. So if you happen to just know that, then you can kind of shortcut this intermediate value. But because I'm trying to construct these things on the fly, I didn't know that. But let's label things. So we have 7, negative 24, and 25. And so you can see like this is actually a reflection. Or you can view this as this, but then rotate it over. Yeah. Good. So now that we have this is our beta. This is our angle beta. And so we can now read off, for part A, sine and cosine. So for part A, this is beta. So sine of beta and cosine of beta. This is what we want. So sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. There we go. And then for part B, indicate the quadrant that the angle belonged to. Yeah, so that's part B. This is quadrant 4. Okay. Right. So the one additional thing I can mention about this would be the formulas. So let me try to find those. I don't know. Okay, I'll just use that. That's fine. Because this is open. Okay. Formula sheet there. Is that the one? Yeah, that's the one. So once this loads up, so the formulas that would correspond to this problem, they're gonna be the pi minus formulas. So I've written them somewhere here. Right, so oh no. There's a way I can do this. How do I do this? Full screen. And hide this. So yeah. Pi minus, supplement formulas, as they're called. So the formula tells you that the sine stays the same, sign. Two different usage of sine. But cosine is going to flip in sign. It's going to have a negative introduced. So that ends up being what we found. The sine, the value for the sine function, stays as negative, but then the cosine function flips. So you could use the formula sheet. The reason I'm kind of hesitant about that is, how is the grader going to know what you did? So, I because one part of the exam is you should show your work, and certainly I will find it difficult to just see you arrive at your answer without any work whatsoever. So I would say that you should write down like what formula you used. That would be a safe thing to do, just so that you actually show your work. Would I dock a point off? I'm not sure. I might. The truth is that I might, because I otherwise I can't tell how you did it, and usually I would assume you copied it from someone. So better to show at least a little bit of work. So maybe in the comment, like you could say, or use supplement formula. But make a note of it on the exam. Okay. Right. So I don't know what else I can say about this. A lot of it is very similar to the past two homeworks that we had. All right. Yeah, guess that's it.